everyone. I'm going to try to give the maximum time to our very special guest today. So I'm not going to have any music, no trivia, just a very quick note about next week. Okay. Next week, Alex is going to come back and we're going to meet at 9:30 a.m. Pacific Standard Time to talk about nested structures. And so I'm really sorry for the time change yet again, because I have a hard stop. To actually give a talk at noon. That's been on my calendar for like months. And so, in consideration of how complicated the assignment is, Alex felt like we should start a little bit earlier just so that he could get through it. And so just a word about one of the assignments for the nested structures. That bias bar assignment is very long and it has like many milestones. I vetted the slides and assignment both by Alex, and then Alex said to make milestone 6 and 7 optional. We did look and make sure all the starter codes are there. And so just try to attempt to get through milestone 1 to 5. And then if you want to attempt 6 and 7, that's fine, but those are optional. And so that's it in terms of assignments for this week. So it is actually an incredible honor to have as our special guest Brahm Kapoor, who is a true legend, I guess, in Code in Place. For those of you who might not have known or heard of Brahm this year, he was actually one of the co-founders along with Chris and Mehran, as well as Ali Malik back in 2020 of Code in Place. And he also, over the years, served as head TA for CS 106A, and also, I believe, the first head TA for Code in Place. And then, in addition, I believe Brahm also helped pioneer and develop the IDE, which is now used in Code in Place, as well as multiple other platforms, including the kind of auto grader. And so he's literally the shoulders on which all of these other giants that we so admire, such as TJ, stand on in order to make Code in Place run. But perhaps what I really admire about Brahm is that over the years, he has volunteered to teach STEM in underserved areas around the world in order to improve educational disparity. And he has won just about every single teaching award that Stanford CS has to offer. And based on what I had heard, his reviews of the teaching bordered on idolization. And so even when I was a TA during my undergrad years, I never got those kind of reviews. And so it's really a pleasure. And thank you very much for taking the time out of your busy schedule to be here today. So with that, I'm going to turn it over to Brahm.
Oh, thank you so much for that introduction. It's probably the most generous introduction I think I've ever received. So I'm honored by that. I was coming in thinking, I don't know if people are going to recognize me, and maybe I do need to do that. If you don't recognize my voice, by the way, I'm coming off like a flu, which is why I sound like this, but I'm fine now and very excited to be here. But apologies if I sip from my tea from time to time. But yeah, I am really, really excited to be here. I'm going to just quickly share my screen as the Zoom interface changes every time I open it, but excellent. Let me know if you don't see my screen, but yeah, as I said, super excited to kind of get this party started and explain to you a little bit about scientific Python. I was reflecting a little bit about like kind of this lesson right before we got started, because it's actually not the first time I've taught this kind of lesson before. Sort of every year since I've begun teaching, in some way or the other, I've taught like what to do after CS 106A or CS 106B, or how to do scientific data visualization kind of class. So I was just looking back at some pictures that people have taken of me or screenshots that I took of myself teaching this. And I can sort of confidently confirm that this is at least the 4th time I've taught this class. And as a fun fact, it's been a different pair of glasses every single time. It's also been a different room every single time. So it's very exciting for me to be sitting here in my apartment in London now, taking you through this. But as my slides sort of suggest, today I'm going to be taking you on a quick tour of how we can use Python for science. This is a style of programming I like to call scientific Python. And I think it's important to start by understanding exactly what it is I mean by scientific Python. And to me, scientific Python is kind of has four important qualities. The first of which is it's numeric, meaning we're doing a lot of math. It's not necessarily complicated math, but math and numbers kind of define what we're doing in our programs. Secondly, scientific Python is conversational, which is probably the biggest difference between the kind of programming you've already done in Code in Place and your programming journey and in science. And when I say that it's conversational, I mean, it's not just a program you run at the start and wait for it to finish, but rather programming becomes part of your process. As you're thinking through how to solve a problem or what information you need to solve a problem, you'll do things like ask questions about your data, and you'll want immediate responses before you decide what piece of code to write next. That'll make a lot more sense when we're actually talking about the code, and I'll show you some of the code I'm writing. But I think it's an important style of programming that might be different than anything you've done before. Scientific Python is also big, meaning that we generally don't just have one number or one string that we're dealing with, but rather thousands or tens of thousands or hundreds of thousands or even millions of pieces of information that we need to process and deal with at the same time. And finally, scientific Python is graphical. And you'll see over here that I've highlighted the text graph, because what I mean over here is not necessarily just drawing rectangles or circles on the screen, as we may have done in graphical programming before, but specifically generating charts and visualizations of data to make your point and to convey the story you're trying to tell. So these are kind of the four qualities I see of scientific Python. Depending on what you're doing, your specific brand of science may not be particularly numeric, or it may not take that much data. But I think if the kind of thing you're doing checks some of these boxes, it's a good hint that you're going to want to think about using the tools that I'll be talking about today. And to that end, there are three tools I'm going to be talking about today. They're Python libraries, meaning they're not part of the core Python programming language, but they pretty much should be, because they're amongst the most popular libraries amongst all of Python users today. Those libraries, their names are NumPy, PANDAS, and Matplotlib. And you might wonder why I've chosen those three libraries to teach today. The first and simple answer is that's what I was asked to teach, and I'm nothing if not happy to sort of provide that. But more importantly, I think they really do encompass the kinds of programming you do when you're doing science in Python, and they really do typify the four qualities I mentioned over here. So before we jump into actually writing some code, let me start by telling you a little bit about, let me move the chat to the other room. And by the way, if you have questions at any point, I will try to monitor the chat just to make sure that I catch all your questions. Feel free to also unmute. To answer the first question, Kapoor with a C is in fact just a different way of spelling Kapoor with a K. It is an unusual way. All right, that said, the first thing we're going to be talking about today, the first library, is a library called NumPy, which I'm pretty sure is short for Numeric Python. And what it fundamentally does is it adds a new data type to Python. We've already talked about lists, and we've already talked about dictionaries. What we're going to be talking about when it comes to NumPy is a type of data structure called an array. Now, we'll get to exactly what an array is, but it adds this new data type to Python, and then it makes that data type really, really easy to work with. Now, one of the things that I think is most impressive about NumPy, and we'll talk about it in a second, is that it's incredibly fast. Now, we already know that the Python programs you and I write by default are really fast and do math faster than you and I could. NumPy is about 50 to 100 times faster than the normal types of Python that we write, which I think is kind of cool. Another thing that's important over here is that the world speaks NumPy. And what I mean by that is that basically any scientific Python library you use is kind of built on top of NumPy, meaning that if you understand NumPy, you understand basically how to provide information to scientific Python libraries of all forms. And I'll kind of try to show you a little bit of that as we jump through this. The next library is a library called PANDAS. I have no idea why it's called PANDAS, but it's a cute name, so I didn't question it. But PANDAS add two more data types to Python. One is called the table or the data frame, which is basically like a spreadsheet. It kind of has rows and columns and allows you to do things with those rows and columns. And then there are series, which essentially are kind of like a single column in a spreadsheet. Again, I'll talk you through exactly how we can use both these things, but they're two new data types, and I find them a really great way to explore large amounts of data. Now, this question over here, now this image over here might seem a little weird to you, but the Olympics just finished. I'm still obsessed with them. So we're going to be using PANDAS today to explore some data that came from the Olympics. And finally, the last library we're going to be talking about today is Matplotlib. It's a library for data visualization in Python. So a library for making graphs and charts and visualizations, and is really, really powerful, and also kind of just the de facto way for doing this sort of thing. I'm not going to say anything about this diagram here, other than to say that by the time we're done together, you will hopefully be able to make a diagram just like this one. All right, I'm going to pause now to see a couple questions over here. The first one, is it true that PANDAS is built on NumPy? It is. PANDAS, like most of scientific Python, does get built on top of NumPy. They tend to be kind of compatible with one another, no matter what versions they're working with, but we're not going to talk too much about that today. The next question is whether NumPy is faster because arrays are faster than standard Python lists. That basically is it. NumPy is actually way faster than Python because arrays are faster than lists, but it's a little deeper than that. It's to do with exactly how arrays are represented in our computer compared to how lists are represented in our computer. And it gets a little deeper than that. We won't be talking too much about that today unless you all are interested. But if you are, happy to go into a little bit of detail as to what makes arrays so much faster. As a fun fact, by the way, PANDAS is a really popular library, but as it so happens, I happen to work in my day job with one of the main people in charge of PANDAS who sort of develops on it on a regular basis. So I told him I was teaching this today, and he said hi. So this class has been blessed by one of the founders and maintainers of PANDAS. All right, so with that in mind, I want to talk a little bit about what we're doing today. I heard that we have about an hour, maybe a little more together, more than that together. So in that hour, I want to show you how to get set up to use these tools by yourself, and then take you on a tour of how I would solve problems with them. And I really do mean how I would solve problems with them, meaning that I have a sense of what I want to do, but I don't haven't already written code. I'm going to be writing that code with you. And so I might be using syntax you don't understand. I'll try to explain that, and I hope you ask questions. But also, if I get stuck or I don't know how to do something or I've forgotten, I'm going to Google it, because I think it's important you see that you can also solve your problems by Googling them. And finally, I want to start to help you develop your muscle memory to solve your own problems using these tools. All of these libraries are massive. I'm not even going to cover 5% of them together, but I hope you sort of understand exactly how, not exactly, but in general, how you might choose to use one of these libraries to solve your problem. All right, so with that said, we're going to get started by actually installing these libraries over here. So as I understand it, everyone, or most of y'all, have at least been developing in Python on your own computers for the past few weeks using PyCharm and Jupyter and so forth. So you should be familiar at the very least with using a terminal and so forth. So the first thing we're going to do is we're going to go ahead and take these two commands over here, the Python 3 command and the Python 3 command over here. Just go ahead and copy and paste those into your terminal. Now, I know you don't actually have access to these slides. Let me see if I can quickly share those with the internet so y'all can copy and paste it. That's not right. All right, let's paste that over here.
Maybe you can copy paste it into the chat.
Yes, I just did that. So go ahead, you can open those up. You should be able to copy that text and paste it in your terminal. I will quickly note that I'm developing on a Mac. So I've written the commands as I would run them on a Mac. If you're on Windows, you should probably replace the text Python 3 with py over here. So please go ahead and install these now if you want. Someone asked a question if you should follow along while I'm coding. I would actually recommend just watching while I'm coding because, I think this is being recorded. You can see it afterwards, and we're going to move relatively quickly. But if you want to follow along, please do. I'm more than happy to kind of answer questions if people are trying, but you absolutely don't need to. All right, so with that in mind, I'm going to go ahead and copy these commands and paste them into my own terminal. All right, I'm going to take a sip of tea while these get installed.
Bram, just a comment, okay? Like normally, we go for as long as 2 hours. I mean, don't feel obligated, you have to do that, but certainly don't feel like you're limited just to that 1 hour time frame as well.
Sure, happy to bleed over.
Okay.
I don't have anything after this, so happy to keep talking. By the way, I know my voice sounds bad. I was sick like 2 weeks ago. I'm totally fine now. My voice just takes forever to recover. So please don't feel like I'm straining myself or anything. My voice is just annoying like this. Alrighty, so I've gone ahead and run these two commands over here. What these have done they've installed the libraries that we're going to be using over here. So NumPy, PANDAS, and Matplotlib are the actual scientific libraries we're going to be using today. And these ones over here, Jupyter, JupyterLab, and so forth, are kind of just to set up the environment we'll be programming in. Now, I understand that y'all talked a little bit about Jupyter before. I'm not going to be reviewing Jupyter again, but I might be showing y'all some new features. So if you have questions about those, feel free to ask them. Someone asked if you can use Google Colab. Please, if you already know how to use Google Colab, you're more than welcome to use these. It should definitely have these ones set up by default. All right, so all the programming we're going to be doing today is going to be in a Jupyter notebook. We're not going to be using PyCharm or the Code in Place IDE or anything like that, because like I said, scientific programming is conversational, and I think the Jupyter notebook environment really lends itself well to that. Okay, so when I asked earlier, I was told that y'all start your Jupyter notebooks by typing this in your terminal, Jupyter notebook. Totally fine. That is normally how you start your Jupyter notebooks. What I'm going to do is type a slightly different command over here. It's called Jupyter Lab. It should just be pre-installed on your computer with the notebook. You shouldn't need to do anything special to get that up there. But when I run that, it basically opens a slightly different looking UI over here. It's got a file explorer on the left like PyCharm does. But other than that, it's going to allow me to edit my Jupyter notebooks exactly the way that you normally would in the normal editor. I should also say, if anyone here is used to editing Jupyter notebooks in another editor like VS Code or PyCharm or whatever, you can totally do that. I'm just using this because it's how I usually write scientific Python. Okay, so let's get started over here. Alrighty, so what we're going to start with is we're going to start by understanding NumPy and a little bit as to how we can work with NumPy. So understanding NumPy. Okay, so definitely the most important line of code you need to know when it comes to NumPy is this line, import NumPy as NP. So what this is basically saying is make all of NumPy's utilities available to me in my Python program, but instead of typing NumPy every time, I just want to type NP instead. This is what's known as a canonical import, meaning that anyone who writes scientific Python code is going to recognize this as the standard way to import NumPy. In fact, if I go to the NumPy website, I would, yep, absolutely. On the front page, that's how they tell you to import NumPy. Import NumPy as NP right over here. Okay, So we're going to go ahead and run this code over here. And what that does is it makes the NumPy libraries available to you in your program. So what does that mean? It now means we can start to create NumPy arrays. So let's talk a little bit about what an array is. And to do that, let's start by talking about probably its closest equivalent in Python, and that is the list. In normal Python, I could do something like this. I can say, oops, nums is equal to 1, 2, 3, 4, and 5. And I now have a list of numbers in Python that I can do things like add to each number and so forth. So for example, if I wanted to write a program which just added 2 to every single number in this list, what I'd need to do is something like for I in index, for I in range when nums.
Hey, Bram, do you
Yep.
mind zooming in on your screen a little bit?
Absolutely.
That way, the people who are watching the recording later could actually see it better.
Yeah, absolutely. Thank you for that. Is this good enough?
Great, thanks.
Great. Thank you very much. I'm on a pretty big monitor, so I'm glad you called that out. Okay, so what I can now do is say something like nums at I plus equals 2, and I can then just look at nums, and I've successfully increased everything by 2 over here. So this is the type of math I'm talking about. I could also multiply every number by 2 by doing something like this, and it would multiply those numbers by 2. That's totally fine. That works great. But when you're talking about, when you're a scientist and you want to quickly add 2 to everything in an array, in a list, or multiply it, like having to write a for loop is kind of annoying. It's not impossible, but having to do this over and over again gets kind of annoying. So what we can do instead of creating a list is we can create what's called a NumPy array, which looks very similar. It's still sort of creating this list of numbers, but then we're passing it into a function called np.array. And what that's going to give us back, instead of a list, is NumPy's new array type, which basically allows us to now treat it not as a list, but instead as an array in NumPy. What that means, that has a couple of important implications. The first of which is we can't now make this list larger by default. We can't do something like nums.append 42. It's going to complain because there's no way to append to a NumPy array. So that's kind of one of the first important things we need to understand about arrays. Arrays are a fixed size. And so under the hood, one of the reasons that NumPy arrays are so much faster than lists is that NumPy arrays can kind of assume that no matter what you do with them, their size isn't going to change. And so there's a lot of speed up that can come from the computer when you can just pick a spot of memory that's that size and not have to worry about ever changing that size afterwards. But now let's say we wanted to add 2 to everything in the list, in the array. Now it becomes super easy. What we can do is say something like nums is equal to nums plus 2. And now if I take a look at nums after that, I've added 2 to every single element in the array just with this command over here. I can also say something like nums is equal to nums times 2. And once again, if I look at nums over here, I've successfully multiplied everything in this list over here, in this array over here by 2 to get this. So this is maybe already feels kind of powerful. It's what we refer to in NumPy as broadcasting, which basically means that when we do something like adding 2 or multiplying 2 to an array, what we're basically going to say is that we are taking that operation and doing it on every single element in the array, which becomes a really powerful operation when we start to think about more complex mathematical operations, as we might do a little bit later on. So that's not to say you can only ever add a single number to an array, you could totally just add two arrays together. So let's say we have something like first nums is equal to np.array 1, 2, 3. And we could say second nums is equal to np.array 4, 5, 6. What we can then say is added nums is equal to first nums plus second nums, and take a look at that. And immediately we see that NumPy has gone ahead and added each element of the array to its corresponding element over here. So for instance, 1 has been added to 4 to get 5 down here. 2 has been added to 5 to get 7 down here. 3 has been added to 6 to get 9 down here, and so forth. So that's kind of like a powerful thing to do, but it starts to get even more impressive than that. So it turns out that arrays don't even need to just be a single row like this. We can have, instead of an array, what in mathematics is called a matrix, which is basically like a table of numbers. So we can say something like, my matrix is equal to np.array. And what we basically want to provide now is a list of rows. So the argument to this function is still a list, but it's now going to be a list of lists. So if I heard correctly in your introduction, you'll be talking more about nested data structures next week. And I apologize if I'm sort of putting the cart before the horse over here. But very briefly, what we're passing in over here is a list whose elements are rows of numbers. So for instance, I can say something like 1, 2, 3, 4, 5 over here, and 6, 7, 8, 9, 10 over here. I'm seeing all of your questions, by the way. They're great questions. I promise I'll get to them. Okay, we can do this. We can create my matrix. And now we'll see that we have a two-dimensional array over here. And by two-dimensional, I mean it has both rows and columns, 1, 6, 2, 7, 3, 8, 4, 9, and 5, 10. Now, in general, when we're talking about dimensions in NumPy, we refer to them as axes rather than dimensions, but you can sort of use those words interchangeably. And what we generally say is that the left to right dimension, the row dimension, is called axis 0, and the up and down dimension, or the columnar dimension, is called axis number 1. Now that'll become relevant in a second, but for now, note that we can do the same things that we were doing with our one-dimensional array. We can add 2 to every single one of them, of its elements. Oops. My matrix. And we can also multiply it by 2. My matrix multiplies by 2. And once we take a look at my matrix over here, you'll notice that we added 2 to 1 to get 3, and then multiplied by 2 to get 6. And we did the same thing with 10. We added 2 to get 12 and multiplied by 2 to get 24. So everything we did for one-dimensional arrays also works for two-dimensional arrays. In fact, it also works with 3 or 4 or 5-dimensional arrays, but that just gets too wacky to see on the screen. So I'm going to stay with 2 for now. Okay. What you can't do, because NumPy is a little stricter than Python, is you can't say something like another matrix is equal to like 1, 2, 3, 4, 5, and then this array is an array of strings. A, B, C. You know, I've actually never tried this, but I strongly suspect it wouldn't work. So let's find out. Oh, no, okay, it did actually work. Okay, so let's see, just out of curiosity, what's happened over here. Okay, so if we take a look over here, what it's done is seen, okay, you had strings over here and numbers over here, but my NumPy array can't actually have both numbers and strings in it. So instead, I'm just going to turn all of these numbers into strings. So we have 1, 2, 3, 4, 5, A, B, C, D, E, all as strings over here. So now I'm kind of curious what will happen if we try to add 2 to it. So let's take a look at that. I kind of have a suspicion, but let's see if that's right. Yeah, okay. So what it basically is saying over here is, hey, I don't know how to add the number 2 to the string A or the string 2 and so forth. So technically you probably can have both strings and numbers when you're creating your array, but NumPy is not gonna let you keep that around for too long. So thank you for the question, whomever that was. Someone else asked about data frames. I'll talk about those in a little bit. I'm glad you've already read about those, but those are actually part of PANDAS, not NumPy. So I promise you we'll get there, but for now we're going to focus on arrays and NumPy. Okay.
Bram, so
Yes.
I had another question. Like, what if
Sure.
you are adding two matrices of different sizes? Will NumPy kind of I guess there's a term, I forget what the term was. Will NumPy like automatically scroll through and then try to recycle elements in the shorter matrices and then add
Yeah.
that to the longer matrices?
Yeah, good question. Short answer is NumPy is not going to let you do that. Let's go ahead and test that out. Let's say my matrix 1 and my matrix 2. And I'll kind of explain why once we've tested that out. So let's say we have these and let's make it just like one. Let's have it just be a single row. Okay. So let's just clean this up and let's try just adding these two. My matrix 1 plus my matrix 2. Okay, so NumPy complains. It says the operands could not be broadcast together with shapes 2, 5, and 4. So the short answer is that when you're doing like adding together or multiplying two matrices or arrays in NumPy, they have to have the same dimensions. And the reason for that is that NumPy basically thinks that if you want to add together two arrays of different dimensions, you probably know more about what you're doing than it does, so you should tell it what to do. So for instance, you described that maybe we should like transpose this matrix and like repeat it across the other one and add it together. And that's perhaps one thing that you might want to do. But someone else might say, you know what? In fact, let's say I want to add 1, 2, 3, 4 to like the top 4 elements, and I want to add 0 everywhere else, or I want to like delete the rest of the array. So what NumPy basically says is, okay, you should go ahead and write that code yourself because I don't want to make a mistake that you don't expect. So thank you for the question, really important one. But NumPy is really, really strict about like kind of what your shapes need to be. And that tends to become a general rule as you stray into scientific Python. A lot of the speed ups and ability to deal with the big data is because scientific Python is a little less lackadaisical than normal Python and it sort of expects better defined operations. Great question. So someone else had the question about a conventional matrix multiplication. NumPy does in fact let you do that. So for context, there is a branch of mathematics called linear algebra, which basically deals all with these sort of matrix types over here. Now, with these matrix types, there are very special ways you can multiply and add them together and do special things with them. So I just want to give an example of that. I'm afraid we don't have time today to do a like full-on linear algebra lesson. So I'm afraid I'll have to leave that to your own time. But know that if there's something that you would like to do in linear algebra, NumPy certainly can support that. So let's create two matrices, my matrix 1 and my matrix 2. Just to make my own life easier, I'm going to make them squares. And let's copy and paste these. Alrighty. Okay. And let's just put some random numbers over here, 43 and 8 or something like that. Now, the way we do, okay, so in linear algebra, the way you would multiply these two arrays together is you would write them next to each other, and then you would like write a dot in between them. Instead of a time sign, you'd have a dot. So that's kind of what NumPy does instead. So NumPy says you need to have my matrix 1, my matrix 2, and then basically literally write the word dot between them. And that's how you multiply these two matrices together. So these numbers probably look kind of weird if you're not used to matrix multiplication, but I promise you they're correct. But for anyone who is familiar with linear algebra, NumPy can do this. Okay, so I hope you're getting the sense that NumPy kind of allows you to express mathematics far more succinctly and expressively than Python does. I don't want to focus too much on like exactly what those mathematics are. There is one last thing I want to show you about NumPy, but before I do that, I want to quickly point out that NumPy has absurdly good documentation exploiting exactly how to do everything in NumPy. I've actually linked it over here in the slides, which I sent in the Zoom chat for anyone who's joined since I sent it. And if someone would mind copying and pasting it again, that would be great. But for instance, they've got a full beginner's guide over here, which explains kind of everything that I've described over here. But if you go to like the full reference guide, for instance, you'll notice that they have a whole bunch of other things you've got. So for instance, there's a full linear algebra section of this document, which allows you to understand how to do different matrix multiplications, like the dot product that I just showed you. There's other like mathematical functions like sine, cosines, and so forth, and so forth. So what I might recommend, and in fact, what I do in my day job is if I'm trying to do like a lot of complex math, I tend to do it in NumPy. Like I use NumPy as my calculator rather than an actual calculator because I'm kind of quicker at typing Python now than I am at typing stuff on a calculator. I also don't think I own a physical calculator anymore. So there's another issue over there. But yeah, before I move on to kind of what I think is the coolest part about NumPy, does anyone have any other questions or anything else that they would like to see? Feel free to unmute or just type it in the chat. All righty, let's see.
Someone asked a question about our NumPy array shapes tuple data type. I don't know what that means, but
Yes, great question. Yes, short answer is yes, but let me kind of explain what that means. So let's take my matrix 1 over here, which as we've seen, oh, that's not right. No, I just copied the one line. All right, so we can do something like this. And now what we can say is my matrix 1, I think it's dot shape. Yeah, okay. So what that does is it gives us back 2, 2 over here. Now this object over here is what's called a tuple. It's another Python data type. It's basically a list, except it's what's known as immutable, meaning that you can't add elements to it, and nor can you change the elements that are inside it. So there's not much more to say than it is a tuple. You can kind of confirm that by doing something like this, and it tells you that it's a tuple. But one kind of cool thing that shows up because it's a tuple, let's actually change this a little bit so it's clearer. So for context, the first element here, or the 0th axis, as I described it before. Whoa, where did I code? Oh, the 0th axis is the number of rows, and the first axis is the number of columns. So what you can say is something like n rows, n calls is equal to that. And then that'll automatically like populate those variables correctly for you. So that's kind of a cool feature of tuples, but really like it's just kind of a trivia fact that they are tuples, and it's pretty uncommon that you'd actually be using the dot shape method in any code that you're writing as a default. Someone else asked a really interesting question about lambda calculus in a private message. It's a little longer than I want to get into for the entire class, but if you want to stick around once we're done here, happy to chat a little bit about that, although I'm by no means an expert on it. Okay, something I did want to quickly talk about, to talk a little about these axes, is that a lot of these functions, when it comes to multi-dimensional arrays over here, can actually operate on a per row or per column basis. So for instance, there's a function called np.mean, which basically computes the additive average of the elements in your array. So for example, if I do np.mean my matrix 1, it will give me back the sum of all of these numbers over here divided by the number of numbers, which is 3.83 apparently. But what I can say is, instead of giving me the sum of all of these numbers, I want this on a per row basis. So I can say something like axis equals 0 and over here. And now what it's going to do is it's going to go across the row, and for each like sort of in the left or right direction or the 0th axis, it's going to give me the mean for each position on that axis. So the mean for like this column over here is 3.5. The mean for this column over here is 4.5. The mean for this column over here is, again, 3.5. And by the way, I should say that I always completely forget which axis is which. I actually had to Google that right before I started lecturing this, because it's just not something that I've ever internalized. But if we said axis equals 1 instead, we would get the average of the first row, which is 2, and then the average of the second row, which is 5.7. Okay, so that's just kind of important, and I think an important thing to know, that you can kind of slice and dice your matrices with just like one row, across rows or across columns. But now the thing that I think is actually really, really cool about NumPy, and maybe the question you're asking yourself is like, why bother learning NumPy? Like, nothing I've shown you over here can't be done in regular Python. Like, you can write a for loop to calculate your means. You can write a for loop to like do it on a row basis or a column basis or whatever. It would just be a little more annoying, but technically you could do it. So what I want to show you now is exactly how much faster NumPy is than normal Python at doing these sorts of things. So what I'm going to do is write some code that actually times Python and times NumPy. So let me go ahead and show you how I'm going to do that. There's a Python module called time, which has many functions, but the function I'm going to be talking about is time, which basically tells me the current time in, I think it's in nanoseconds, it might be milliseconds. I can't do the math in my head right now, but you'll notice right now it's like 440, and when I refresh, it becomes 457. If I refresh again, it becomes 60. Okay, so this is probably seconds, and then this would be 1, 2, 3, 4, 5, 6, 7. So millionths of a second. So very small numbers is basically my point over here. So what does that mean? That means we could do something like this. Time 1 is equal to time.time. Time 2 is equal to time.time. And in the middle, we can write some code. So we can, for instance, say for I in range 100, or, you know, let's just I equals I times 2. Let's just multiply each number by 2. And then what we can say is duration is equal to time, time 1 minus time 2. And take a look at the duration. Okay. Oh, whoops, let's change that around. Okay, so you'll see, for instance, that multiplying each of the numbers from 1 to 100 in normal Python took like e to the -5 times 8 seconds, which basically means 0.1234 it took this long, essentially. Oh, sorry, that's 1 too many zeros. It took this many seconds for Python to multiply 1 to 100 by 2, or 0 to 100 by 2, which is pretty fast, and, you know, probably not a problem. But what I want to do is something a little more complex. What I want to say is I want to add together every number from 1 to 10 million. So let's go ahead and do that. let's say that the total is 0. And then for I in range 1, 2, 3, 4, 5, 6, 7, total plus equals I. And you know what? Let's not even actually look at, like, print out the duration right now. I don't want to spoil the surprise. Let's just say that Python duration is equal to this. Okay, great. Let's run that. And you may have seen, I'll run it again in a second, but take a look at this number 40 over here. It's going to turn into a star while the program is running, and then it's going to stop afterwards. Okay, so it was a star for like a second or something like that. So Python it was very fast, but it took like a noticeable amount of time to add those two numbers together. Okay, let's now do the same thing in NumPy. So the first thing I'm going to do is I'm going to go ahead and create my array. So let's say that numbers is equal to np.array list range 1, 1. Okay, I'm going to copy the paste the number so you know I'm not cheating. Okay, so there's my numbers. One more parentheses. Okay, so I created my numbers. Let's go ahead now and do the same thing over here. Let's copy and paste this. Let's say now instead of all of this, all we're going to do is np.sum of numbers. And we'll say that NumPy duration is equal to time 2 minus time 1. Okay, so pretty much exactly the same thing. The only thing that's changing is instead of the for loop over here, I'm just calling the NumPy method on the NumPy array. Let's go ahead and run that. Again, take a look at the star over here. I didn't even see the star. I'm sharing my screen. You may thought it had vanished. I literally did not even see the star on my screen before it was replaced with this number over here. So let's go ahead now and do this. Print the time it took in Python was Python duration seconds. And copy and paste that. And got to turn it by strings. Let's do the same thing in NumPy. Duration seconds. And then just to like fully flex, let's say NumPy was NumPy duration divided by Python duration. Times faster than Python. Alrighty.
Should probably be the other way around, like Python divided by NumPy.
You are totally right. Thank you. And that leads to a way more impressive print statement as well. So I'm glad you pointed that out. And that would have been so much cooler if I remember that parentheses. Alrighty. So the time it took Python was 0.5 seconds. The time it took NumPy was 0.019 seconds. So NumPy was about 25 times faster than Python in this particular case. Now, I have seen other cases where NumPy was something like 200 times faster than Python. It really depends a little bit on like what computer you're using and a few other things that are happening under the hood. But at a very high level, you can generally expect NumPy to be tens of times faster than Python at basically any mathematical operation you can think of. So if nothing else matters, this will. Now, someone sort of preempted the next question, why you'd care about this difference over here. For something like this, even though it's a 25x speed up, it probably is not that meaningful, if it's taking 0.5 or 0.01 seconds. But there can be types of math, for instance, if you're doing, matrix multiplications or finding square roots or exponentiating numbers or so forth, where you will actually see those numbers start to climb up. Unfortunately, every example I could think of, I have a pretty beefy Mac right now. So my Mac's pretty fast at everything. If you're fortunate enough to be in that position, you may not need NumPy specifically for things like this. But I think the kind of ceiling deal for NumPy is it makes the math a lot easier syntactically if you're doing sort of array or matrix mathematics, but also that like when it comes to dealing with really large data, and I will say that even 10 million is pretty small in computer language, NumPy tends to be faster. But the most important reason I'm spending so much time on this is because every single thing that you use in scientific Python is going to be built on top of NumPy, because NumPy is so much faster than normal Python. When we start to talk about libraries for instance, creating neural networks or large language models or so forth, all of those will use NumPy under the hood because it is so much faster than PANDAS or than Python or anything like that. Okay, any final questions about NumPy before we move to PANDAS?
Yeah, I had one question having to do with greater than two-dimensional arrays. I got really confused because in my mind, I started making an analogy between a 3D plot, okay? And then when I started to see that when you get into a quote 3D, I think technically it would be the third axis, is stacking two-dimensional arrays. And that was really confusing to me. And even though you said NumPy likes to use the axes, you read all the time that it's a three-dimensional array or a 4D. Can you say something about that?
Yeah, absolutely. No, it's a great question. Maybe what I should do is create a 3D array, which it's also going to be the first time I think I've done that this way. So give me a second to find a good example over here. Okay. So let's go ahead and, you know what, we're going to make this array is a square. And I hope it's sort of obvious that this array is a square over here. It has 2 rows and 2 columns. What I'm going to do is I'm going to make a cube. So if we think about a cube, like, you know, imagine like a 2x2 Rubik's Cube or something like that. It's basically a square of 4 on top of another square of 4 over here. So what I can do is I will basically create another square of 4 right on top of this one over here. And I'll fill that with like much larger numbers. So that becomes a lot clearer. 90 and I don't know, 42. Okay. So what we're talking about here is we're now going to have a cube of numbers. And you can kind of imagine that the top layer of numbers is 1, 2, 6, 7. And then the layer below it is 100, 1000, 90, 42. Again, like I said, I got the axes. I kind of confused in my head. So I'm pretty sure that's what NumPy is going to reflect it as. But if we take a look over here, oh, what did I miss? Sorry, there needs to be another list around this. And this, in fact, turns it from a 2D list to a 3D list, which is kind of scary. But yeah, okay. So if we take a look at this, we'll see that array is like the top layer of that cube is 1, 2, 6, 7, and the layer below it is 100, 1000, 90, 42. And we can start to take means of those. So we can say, for instance, np.mean array axis equals 0. Oh, what did I call it? My matrix. Okay, so you'll see that what this has done is this has taken the average of like, and it maybe doesn't make sense to think of it as rows and columns anymore, but it's taken the average of 1 and 100 to get 50.5, 1 and 1000, 2 and 1000 to get 501, and so forth. If we do axis equals 2, it's taking the average of 1 and 2 to get 1.5, 6 and 7 to get 6.5, and so forth. Axis equals 3. Oh, sorry. And if I do axis equals 1, it's taking the average of 1 and 6 to get 3.5 and so forth. So so like I said, this gets like really confusing to conceptualize. I think it's easy to just start to draw things around. What I will say though is when you start to deal with three-dimensional data, at least in my experience, it tends to be when you're doing sort of like pretty complex data science or machine learning or something like that. And in those cases, your dimensions tend to have like actual meaning. So you might use a 3D array to represent a movie or something like that, where the rows and columns are each frame of the movie. And then as you go back in the 3D array, that's like each successive frame in the movie or things like that. So it becomes easier when you sort of have a use case behind it to assign a meaning to the dimensions rather than thinking about them as rows or columns or anything like that. So basically, I think the big takeaways with NumPy over here is it looks very foreign when you start to write it for the first time, but you very quickly develop a muscle memory for it. So I'd encourage you, even if you're feeling a little bullish on NumPy, to give it a shot with a couple problems that you're trying to solve. I think you'll find that you'll start getting a lot quicker at it. And for instance, for me, I don't find NumPy any slower to write now than I do normal Python, which is why I use it instead of normal Python to do mathematics. Okay, I do want to move on now to pandas. If anyone has any other questions about NumPy, happy to take those at the end. On axes and dimensions, sorry if I didn't mention it. If we kind of talk a little bit about axes and dimensions, you can roughly consider them as synonymous, but I think the mistake one makes is thinking of dimensions in terms of like our human spatial dimensions. Like NumPy doesn't have a notion of like left to right, up and down, back and forth, or anything like that. It only thinks of dimensions as the zeroth dimension, first dimension, and second dimension, which is why I'd say that in general, like it's far more helpful to think of the dimensions or axes of your NumPy matrices in terms of like what they actually represent, like the rows and columns of your image or like the frame number in your movie and so forth. As hard as it might be, I'd really encourage you to step away from thinking about it in terms of like, this is the matrix I've got pictured before me and I'm moving to the right or moving back and forth, because that way lies dragons, I'm afraid, with pandas, with NumPy. All of that said, I will quickly note that like, other than like off the cuff mathematics, when I'm writing scientific Python on like a regular basis, I tend not to use NumPy directly because far more often I'm using something like pandas or another library that's built on top of NumPy. So if, for instance, you're a researcher doing research, you may not necessarily find yourself directly importing NumPy, but I do think it's important to understand why it's so much more powerful than anything else. So let's talk now about pandas. Import pandas as, oops, understanding pandas. Okay, great. So let's go ahead and start with the canonical import for pandas, which is import pandas as PD. Okay, so what this is basically doing is the same thing over here. It's importing NumPy and it's allowing you to use it and call it PD everywhere in your code. So I want to start now by talking to you a little bit about a problem I'm actually kind of interested in exploring over here. So earlier today, I went online and I downloaded a bunch of data sheets over here to do with the Olympics that just finished. So for instance, if I open athletes.csv over here, it'll take a second to open, but it's basically just a big spreadsheet of information about the athletes. So for instance, there's this athlete over here from Armenia who, was a wrestler who participated in the men's Greco-Roman 97 kilo, was born in 1991. There's basically just a bunch of information about them. I don't know if anyone else was following the Olympics or like going online and reading about the athletes, but it's kind of cute. They've got like fun facts about the athletes and stuff over here as well. So I was kind of interested in understanding a little more about athletes, and I thought that this class might be a good way of doing that. So the first thing I want to do, because I never really learned to use Excel particularly meaningfully, is I want to bring this into Python. I want to deal with this spreadsheet in Python. And the way we do that is with pandas. So there's a line of code, pd.read CSV. And what this line of code does is it takes the name of a spreadsheet, athletes.csv, for example, and it then turns it into a Python data structure for you to use. So exactly what file name am I going to pass in? You'll notice over here that I'm in untitled1.ipynb, and my file is athletes.csv, which is in the data folder over here. So what I'm going to do, therefore, is I'm going to type in data/athletes.csv. I'm going to enter that, and boom, I've now got it in Python. Someone asked what the correct order of operations is, like whether we have to open the file first or anything. Pandas does all of that for you. It immediately turns this file over here into this data frame in Python, which now means I can close this tab. I never need to look at the raw file again. But it does have all the same information, and it read that entire file really quickly. I can immediately see 11,000 rows and 11,000 rows in this. So there must have been 11,000 athletes at the Olympics and 35 columns. Someone's asking what you do if you have bad or missing data in your CSV. Short answer is it kind of depends on how bad it is. If, for instance, you're just missing some fields or some numbers, something that should be a number is a string instead or something, pandas can usually deal with that and will just kind of say, hey, this wasn't a number, but I'm going to mark it as not a number over here. Sometimes it may be worse, like your file may be corrupted or your data might just be really bad. In that case, unfortunately, you have to fix it before you get to pandas. There are some libraries for doing that, but a lot of this tends to be just like human, like looking through data and cleaning it up. One important note I wanted to mention is this CSV file format over here, which is not, of course, what you'd be saving your files at if you were using like Excel or Numbers or something, Numbers being the Mac version. All these softwares, every single spreadsheet software I've seen has the option to export your spreadsheet as CSV. So I strongly recommend if you want to read it into pandas doing that. I think pandas might also have functions for like reading Excel files directly or reading Numbers files directly, but I haven't personally used that. But I'm sure we can Google it and see. Pandas read Excel. Yeah, okay, cool. So pandas does in fact have a read Excel file. So you probably should be able to just read, like pass in a string file path as to like, athletes.xlsx, I think is the extension. And that would probably work if you change this to Excel. But unfortunately, not an Excel expert, so not gonna pine very much on that. On the data cleaning process, because it seems like there's a bunch of other questions about that. I'm sure there are tutorials online as to like generally how you can approach cleaning data and so forth. But every time I've had to do it, it's been like a very specific to that use case process. Like I would try to read it into pandas and I'd see, oh, this column is messed up, this other column is messed up, and then I would either fix it manually or I would like write a Python program to fix it for me or something like that. So unfortunately, there's no like one size fits all approach over here. Okay, so what's important over here is that this data structure we're looking at over here, this Python table is what's called a data frame. Someone asked a question about data frames before. And if we take a look at type over here, you'll see that we get back a pandas data frame. So the data frame is one of the two important data types that Python, that pandas adds to Python. So typically, we shorten that in Python to df. So we can say something like athletes df is equal to this. And now we have this stored in a variable. Now, I want to take you through kind of how I would explore this data. One function I could use to quickly like get a sense as to like what the data looks over here is I could call a function called head, which just gives me back the first 5 rows of the data file. And if you take a look now, I can sort of quickly skim this and notice some things about it. So for instance, it looks like, whoa, didn't mean to do that. Yeah, so for instance, it looks like sometimes people's families aren't like provided for whatever reason. Probably the athlete didn't fill out the form. They probably didn't fill out the form for like what their reason is or who their hero is and so forth. Some of them may not have sporting relatives. If I want to take a look at more of the data, I can say like 10 or something. It'll show me 10 rows instead of 5 rows, which I think is also really helpful. Another thing that I might find helpful is just looking at the columns over here. So I can say, for instance, okay, what are the columns of this table? And I can see, okay, you know, there's their name, their country, their nationality, which disciplines they were in, but also, you know, if I'm interested, their height and their weight, and so forth, which, you know, may be interesting. So for instance, let's say that I wanted to learn a little more about the heights of the athletes. So if I take a look again at what I can say is something like, okay, I want to take a look at just the names of the athletes and their heights. So I can do that. And what I'm basically doing now is I'm treating the data frame a little bit like a dictionary, but I'm passing into it the names of all of the columns that I'm interested in looking at. If I take a look at this now, it gives me the heights of just the names and the name and height columns of all these athletes over here, which I think is kind of cool. You know, I could also add, I don't know, their weight column, and it would give me that as well. So I'm not really doing anything in particular right now. I'm just kind of looking at the data. So I'm seeing, for instance, over here, okay, it seems like either there were a lot of really short athletes or a lot of athletes just didn't provide their data in the first place. So maybe it might be interesting to look at like who did provide their heights and what their heights kind of looked like over here. So how can I do that? Well, let's go down over here and let's take a look at just the height point of the height column of the athletes. Oh, athletes GF, sorry. Okay, cool. So you'll notice this looks a little different to this data frame up here. So let's start by figuring out what this data frame, what this type actually is. It's what's called a series in PANDAS, and it is the second important data type that PANDAS adds to Python. And by series, what we basically mean is a column of data. So if we take a look at this, it's a column of data that starts at the same height as over here, 0, and ends with the same height as down here, 0, and has 165 before it as well. It's also, because it's kind of more just a list than anything else, it's also indexed. So this on the left over here is what we call the index of the series. So I can say, for instance, give me the, what was that, 11107th element, and it'll give me back just that 174 over here. So that's just a point of curiosity, not necessarily something you'd be doing that often. But what is kind of interesting about this is that just like NumPy, and in fact, because under the hood, this is built on top of NumPy, this supports broadcasting. So if I wanted, I don't know why I would, but I could add 2 to every single athlete's height. I would add 2 to everything. But what's kind of more interesting is I could compare that height to another value. So I can say, for instance, which athletes had a height that wasn't equal to 0 over here. So there's kind of two important things that's going on over here. The first of which is you'll notice that we've now turned it from numbers over here to booleans. So we're now saying that like 0 is equal to 0 over here. 165 is not equal to 0. So we got a false up here and a true over here. So we immediately kind of have this Boolean array as well. So someone asked how a series is different from an array. I think for the most part, you can kind of treat it as a one-dimensional array. A series, to my knowledge, cannot be multi-dimensional. So it can't have like rows and columns or anything like that. As soon as it has rows and columns, you're talking about a data frame, no longer an array. And yeah, I think that's probably the main difference between series and arrays. Typically, you tend to find yourself doing less math on series, although depending on what it is exactly you're doing, you may still find yourself doing that. Excellent. So here's what's really cool about this, though. What this false and true has also done is it provides us a way to now extract only the athletes in this original data frame over here who have heights that are not equal to 0. So for instance, I can say athletes df and index into this. Now what this is going to do is it's going to say, okay, first go ahead and compute this little series over here. So give me back like 0 for false, 1 for false, 2 for false, and then like 11,108 for true. And then only keep the rows whose value is true over here. So you'll see, for instance, that when we finish this, we're going to have a much smaller data frame. So let's just quickly remind ourselves over here that like Chalangat and Ada Ito are two athletes over here who have non-zero heights. And when I run this, you'll now see that Chalangat and Ada Ito are still the last two athletes with non-zero heights, but we now only have 5,078 rows rather than 11,000 over here. So in just this one line of code over here, we've completely filtered out all the athletes for whom we don't have height data at all, which I think is really cool. So let's put this in a variable as well. Athletes with height equals this. And once again, we can just do athletes with height. We can take a look at the height column over here. And you'll notice that we no longer have non-zero columns anywhere over here. We non-zero heights, we only have 0 heights, which I think is like, we only have non-zero heights, which I think is really cool. Okay, so there's even more we can do with this. And now we have just the non-zero heights. So I can kind of be like, okay, I want to know a little more about heights. Like I can kind of imagine that like as athletes, Olympians might be relatively tall, but also like, you know, there are gymnasts and stuff who generally are not that tall. So maybe they skew the mean. So there's a function over here called .describe, which what that does is it takes that height series I just showed you and it gives me a bunch of information about it. So for instance, the mean height for an Olympian is 178.9 centimeters, which is kind of actually fun because that's basically exactly my height. The shortest athlete was 1.4 meters, and the tallest athlete was 222 centimeters tall, which is really, really tall. So maybe the next question I'd ask myself is, who was the 2.2 meter tall behemoth? So let's take a look at how we can do that. We can say, for instance, sorry, I lost my cursor for a second. Okay, we could say something like, first of all, what was the max height over here? So dot max, oh, sorry, that should be a function. And that's going to give you back, okay, the maximum height of this series is 222. And then what I can then say is, okay, so now tell me, let's go ahead and tell me of all the athletes sorry, let me. Okay, so now go ahead and tell me, of all the athletes, how many athletes were there whose heights were actually the maximum over here? So how many people had a height that was equal to 222? And as you can imagine, most of the athletes were not 222 centimeters tall. But what I might want to do again is say, okay, give me only the athletes who actually were 222 centimeters tall. So athletes with height at this. So now what this is saying is, give me back this same series over here, which is mostly false, but has at least one true for the person who is in fact 222 centimeters tall. And then give me back only the rows of those people. So when I run that, we get our athlete who's 222 centimeters tall. So you'll see, for instance, that, oh, okay, it's Victor Wembanyama, who's the NBA player. I could have probably guessed that it was an NBA or basketball player, and I know he is really tall, so this isn't surprising to me. But yeah, I think this is a pretty cool way to do this. I actually think, and so this is where I'm sort of going to be upfront and I'm saying there's probably an easier way to do this as well. I would guess, because I'm sort of familiar with NumPy, it'll be something like athletes with height dot max column equals height. Again, fully guessing, not sure if that's correct or not. Okay, yeah, doesn't seem like it liked that. But anyway, that was just a speculation. But I just wanted to test that out. So ignore I said that, but hopefully this is a pretty simple thing. So what I want to point out over here, though, is that what I'm doing over here is I'm not necessarily like, I don't have a hypothesis I'm working towards. I'm not trying to like prove something. I'm just trying to understand my data. And one of the gaps that might be popping out over here is like I can maybe only get so far if I'm only looking at numbers. Like if I look at athletes with height over here, if I look at their height over here, you'll see, okay, cool, I'm looking at numbers, don't really know what to do with these numbers. It would be helpful, for example, to get like a histogram or a plot or something of exactly what their heights look like. And as it turns out, pandas can help you with this. So what I can say, for instance, is something like dot hist, and then say bins equals 30, which is basically saying, okay, give me back a histogram of all of the heights and slot it into 30 equally spaced bins. If I run enter over there, it's going to take a second because remember, it went over 5,000 athletes, but here now is a histogram of every single athlete's height at the Olympics in Paris in 2024. So you'll notice there's Wembanyama right there at the very end, and whoever the shortest athlete is over here. But the bulk of them tend to hover at around like maybe 175 centimeters or something like that, which is a kind of cool. So what's actually happening under the hood over here is we've seen the first use of the third library I'm going to be talking about today, Matplotlib. I'm not going to talk about Matplotlib yet. I'm going to keep treating this as a pandas feature for now, but we will jump deeper into the Matplotlib stuff in just a little bit. Okay, cool. So there is some basic data exploration. I'm going to do a lot more because I think it's powerful and honestly just kind of fun. But before we move on, anyone have any questions about how we've used pandas so far? I'll give you a second to come off mute. Okay.
There's a
Yes.
question in the chat. It says, can we do conditional formatting in Panda like the spreadsheet use Boolean logic? I'm guessing yes, but
Did we do conditional formatting in pandas? Yeah, that's an interesting question. So again, not super familiar with spreadsheets, but by conditional formatting, I would imagine you mean the sort of thing where like make this green or bold if it's greater than 50 or red if it's less than 25 or something. If I'm wrong about that, please do let me know. That's not really a thing in Pandas because like Pandas is like a library about the data, not how the data is presented on your screen. So if I take a look at athletes with height over here, I'm getting this nice table over here because Jupyter Notebook is giving me this nice table over here. In fact, like Pandas itself doesn't really know how to make the table look like this. Under the hood, it probably looks way more messy. There are some ways to do this. So for instance, you can write some code that like exports your Pandas data frame to a PDF or to an HTML file or something like that, and apply that conditional logic to the HTML that's being generated. But I'm not going to talk very much about that today. And I don't personally know how to do it. I need to Google how to do that. But when we're just talking about in the Jupyter Notebook environment, no. Oh, okay. So I think we got clarity. Round up all data into two numbers, pass the decimal format. So Pandas definitely can round. I don't know if it can do that just to like show it to you on the screen because again, it's not so much about the presentation of it, but Pandas definitely has ways to round your data. Unfortunately, all of this data is already pretty round, so I can't round it anymore. Financial tables. Pandas doesn't have the abilities to like render financial tables on the screen, but it does have a lot of financial operations. So finance functions, I guess. Yeah, so if you take a look at the documentation, they do have a bunch of things for like, you know, computing samples or computing rolling means and so forth. The company I work at is a financial company, and we use Pandas extensively for like financial stuff, but not necessarily for like actuarial information. So Pandas isn't necessarily going to be able to convert between currencies and things like that, because again, it's way more about just like presenting the data and exploring it than it is about rendering or like looking out to currency exchange tables and so forth. Someone else asked if I'm explicitly calling the float64 data type or if it's a default. I think they were referring to this, athletes with height. Okay, so now, for instance, you'll see down here that it says int64. I think earlier I had float64 for the average or something like that. This is happening by default. When Pandas read that initial screen spreadsheet, it saw that everything over here was a number, so it called it an int64. If we start doing math that turns it into decimal numbers, it will infer that you need float64s instead. That 64, by the way, is just like a representation under the hood of how that number is stored. And it also comes from NumPy. So there's another way that NumPy is kind of bleeding into the Pandas world a little bit. Excellent. So now I'm kind of interested. I should say in general, I'm a bit of like a geography nerd. I'm fascinated by countries and those sorts of things. So one of the things I'm kind of curious about, if we look at our athletes over here, is how it, like exactly what the country distributions looked like. I watched the Olympic opening ceremony, and you know, some of the boats had like just 600 athletes from one country, then other boats had like 4 athletes from 4 countries because they were sending way fewer. And I'm curious, I'm kind of curious like exactly what that looked like. So let's take a look then just at the country column over here. So I can do something like athletes.country. Oh, it's athletes.tf.country. Again, I get a series. It's not a numeric series this time. It's a series of strings or of objects. But you'll see we've got a bunch of Armenias, we've got a bunch of Italys and so forth. So yeah, that is like that's our series over here. And maybe it might be interesting to start by just like looking at how many of each country there were. So turns out there is another thing Pandas gives us. It's called the value counts method over here. And what that basically does is it quickly counts by each country over here and tells how many there were. So immediately in descending order, we sent the US and the most athletes at 619, and very narrowly following them was France with 600 over here, which, makes sense. France gets to send an athlete to every sport because they hosted. Then was Australia with a pretty big contingent, and then Germany and so forth. But now it might also be interesting to kind of plot what this looks like. So I could do something like dot plot. And, I think an interesting graph type over here, rather than just like a bar chart or a histogram or whatever, would be a pie chart. So I'm going to say dot pie, print that out, and boom, here is every single country at the Olympics plotted. So you'll see the US was sort of the biggest chunk over here. France was next, Australia next, all the way to Great Britain over here, and so forth. But you'll also notice this is kind of a crowded chart. There is, I don't know how many countries sent, probably 200 and something, sent athletes over here, and that's kind of a lot. So let's say instead of plotting all the countries, we only plot like, I don't know, the top 30 countries or something like that. That makes it a little easier. I'm using that same .head function I used up here to get the first few rows over here. Oh, no, I no longer have it over here. But anyway, I'm using that function. I'm getting the first 30 countries. I'm plotting them, and then I'm getting a pie chart over there, which again is kind of cool. If instead of a pie chart, I wanted a bar chart, no problem. I get a bar chart just by changing .pie to .bar over here. So yeah, I think that's pretty powerful. We're going to go a little further with this in just a second. But does anyone have any questions about this before we move on about these two new plots? I do see some other questions in the chat, so I'll take those first while you all unmute yourself and so forth. Okay, so can NumPy get user input to create a data frame? Could it be used as a kind of spreadsheet where you enter a delimited number of rows and columns and do things like summing the rows? You totally can. What you'd probably need to do in that case is write a Python program that like collects the user input however you want it to, and then stores it in a bunch of lists or a dictionary or whatever, and then turn it into a data frame afterwards. There are methods in Pandas to turn stuff into data frames from dictionaries or from lists of lists. Again, the Pandas documentation is also shockingly good and is linked over here, so I'd encourage you to check that out. But yes, so absolutely that is possible. I will say though, in practice, every time I've ever used Pandas, it's been like me downloading some information or me collecting some information, having it in a spreadsheet file, and then reading that into Pandas. Thanks for the question. Anyone wondering anything else?
Where do you get your data? Because there's so much data missing.
Yeah, great question. Someone else asked this earlier on. I was just trying to figure out somewhere to get interesting Olympic data, but it turns out I went where a lot of data on the internet lives. It's called Cackle. It's basically a website for people who want to do things with data on the internet. So they have like a bunch of like machine learning stuff and a bunch of code that you can read. But the thing I like the most is this list over here, this tab over here called datasets, where currently the most trending data frame is the 2024 Summer Olympic Games dataset, which is what I used, but they have like a ton of different things. So I don't know. Yeah, I was looking at movie data as well. They have a data set that's 50,000 movie reviews and so forth. So this is generally a good place to look. Another thing that I think is kind of interesting is a lot of governments all over the world publish data in some way or the other. So another data set I've played with before relates to another interest of mine, which is that I'm fascinated by public transport. So London's sort of public transport management agency publishes a bunch of data and APIs online, which allow you to download like passenger data and train schedule data and so forth. So if you're looking for kind of like official data, government websites, the UN, the World Health Organization, those sorts of institutions tend to publish it. If anyone here is in America and in New York specifically, New York City is also really, really good about sort of openly publishing data. But really, I think like the main tool over here is like pick something you're interested in. Let's say like rock climbing. That's like my favorite sport. Rock climbing data set. Google that, and there, lo and behold, Kaggle has some sort of data about climbing. I don't know what it is right now. Kaggle, you do need to make an account on it, but I think basically everything is free once you have the account. So definitely use that as a big resource. Great, thanks for the question. Anyone have any other questions? Excellent. So there's a couple other things I want to show off in NumPy in pandas. The first of which is you may have seen that there was a height column in the data frame. There's also a weight column in the data frame. Athletes weight. Athletes df dot weight. Again, it seems like there's a lot of zeros over there. So maybe I might want to like filter down. Oh, someone asked if you can follow me on Kaggle. I mean, you can. I don't really do anything on Kaggle other than download data sets. So it would be a pretty boring follow, but sure, you're more than welcome to. Anyway, so for the next thing I think I'm interested in plotting, I think it'd be interesting to see kind of like the height weight distribution of athletes at the Olympics. Because, I would imagine most of people are kind of somewhere in the middle, but you'll have like your wrestlers or your weightlifters who I imagine would be way heavier, and then your gymnasts or your rock climbers or your high jumpers, I suppose, who might be lighter. So I might be interested in taking a look at how to do that. So what I want there, though, is I only want data for whom athletes have, I only want athletes for whom I have both height and weight data. So let's go ahead and do that. Let's start by saying athletes. And what I want to do now is index into the athletes data frame and only get back the athletes whose heights and weights are greater than 0. So I can do something like athletes height is greater than 0. And I'm using the % over here. Athletes.weight is greater than 0. So I'm doing basically the same thing I did up here, where I'm getting a bunch of trues and falses, and I'm indexing into it over here. In this particular case, you know what? Maybe it would be helpful if I first showed you just this thing over here. So if I take athletes.height, it's greater than 0. Athletes df. You'll see that's a bunch of trues and falses. I can then compose it with athletes.weight is greater than 0. And I now get a bunch more falses because clearly the athletes whose heights I did have, I don't have weights for. What's happening to my notebook? Okay. But hopefully there are some athletes. I actually don't know if there are any athletes for whom we have height and weight. I'm hoping there are, but now we can index into that. Excellent. Okay. So we have 316 athletes, which is kind of not as many as I would have expected, but fair enough. Can't argue with that. So these are the athletes for whom we do have heights and weights. So let's go ahead and store that. Athletes with heights and weights is equal to that. And now let's take a look at just at their names, their heights, and their weights. Cool. Alrighty. So for instance, Harry McNulty is 185 centimeters, weighs 98 kilos, I assume. 98 pounds sounds a little light for someone that tall. And we have someone else who's 102 kilos, someone else who's 75 kilos, and so forth. But I'm kind of interested in viewing the like a scatter plot of this. So what I can do instead is call the same plot function over here. I can then say I want a scatter graph. And then I want to say, okay, let's say that the x-axis of my scatter chart is height. And the y-axis of my scatter chart is weight, which are the names of my columns over here. Wow, I really did that wrong. Excellent. Here's our scatter plot of all the athletes for whom we have heights and weights, and a scatter plot of that. So over here is Victor Wembanyama, who is very tall, but surprisingly not the heaviest person, and someone else who is the heaviest person, but still like 190 something centimeters. Okay, so all these plots I'm showing you over here are using are using Matplotlib under the hood. So if you use pandas to do your pyplot, to do all of your plotting, then you may not need to write pandas directly. You may not need to write Matplotlib code directly. That said, if you start to like customize this graph in any way, like you want to add colors or a legend or so forth, you start to have to concern yourself with the Matplotlib part of it. So it's really helpful to be familiar with Matplotlib, even if you don't like use it. Someone in a question mentioned Seaborn. Seaborn is another library in Python. I'm not going to talk very much about it, other than to say it's kind of styling on top of charts. Like this isn't a particularly pretty chart, blue on white is a little garish. Seaborn allows you a bunch of ways to like style your chart, so it's kind of more visually appealing. At least that's what I've used it for. It may also have its own plotting functionality, but like for me, I use it basically entirely to make my charts prettier. Okay, so that's that. I think there's one last one last thing that I do want to show over here, which is that you may have seen that I only had this one chart. I only have been looking at this one data frame over here, athletes.csv. But it turns out there are a bunch of other charts as well, like medals total.csv, for example, which shows how many medals every country won. The US won 126 total, China won 90 total, and if we go all the way down, Zambia won 1 total. You'll notice there's only 92 countries over here because apparently not every country won a medal, but still Olympian, so that's cool. But let's see now if there's something we could explore over there. So for instance, like, the athletes, 126 medals won by the US is pretty impressive, but that was also what, like 600 athletes or something like that. So I'm kind of curious now whether the US still comes out on top if we control for how many athletes were actually from the US. Like Hungary won 19, but may like just have had only 2 athletes or something who won a bunch of medals each. So I'm kind of curious to see like what that balance looks like. So the first thing we need to do is go ahead and read this into pandas as well. So the way I'm going to do that is I'm going to say something like, I don't know, medal counts equals pd.read csv data / medals total.csv, and do that. If we take a look at medal counts, just to prove it to you now, there's the same table we saw, USA 126 all the way to Zambia at 1. And now what might be interesting to do is figure out a way to like join or combine the data we have in medal counts with the data we have in athletes. You know what? I'm making this mistake too often. I'm just going to create a variable called athletes so I don't have that problem anymore. So this table over here is the table whereby I can actually figure out how many athletes there were per country. Once I know that, I can then say, okay, let's go ahead and combine that with this table over here to kind of find out how many athletes there were per country. So let's go ahead and do that. Let's say something like, what I'd like is something called per country counts, where basically it's a table which has the name of the country code as well, because that's what we have in this table over here. And then just how many athletes there were from that country. I don't care about their names, their heights, their weights, and so forth. So what we're going to therefore need to do is we're going to need to combine data from the medals total file as well as the athletes file, and we're going to do that in Python. So let's start by getting the counts per country. What we're going to want to do is group this data over here by the size of, by like the name of the country. So there's a pandas function for that. It's athletes.groupBy, and then we provide a list of which columns exactly we're going to be grouping by. So in this case, I'm interested in the country code and country columns over here. So let's go ahead and write those. Country and country counts. A good way of kind of reasoning about this parameter is it's which columns you want to stick around in your new table, because we're going to be doing a bunch of counting and stuff, but I don't want to count the number of countries or the number of country code. Sorry, that's a typo. What I do want to count is inside each country, how many athletes there were and so forth. So I can do that. Then I can do dot size. And let's take a look at per country counts. Per country counts. And boom, just like that, I now have, this is actually a series, not a data frame, but it's a series where I can index either by country or by country code. And I can say, okay, for instance, Afghanistan had 6 athletes, Algeria had 46 athletes, Zimbabwe had 7 athletes, and so forth. So kind of cool. Pandas did that really quickly. It went through 11,000 rows and I did those counts really quickly. What I actually want though is I don't want a series of just the counts over here. I want a data frame. I want a table whose columns are country, country code, and number of people. So the way you do that is through one of Pandas' most like enigmatic methods, which is the reset index method over here. So what I'm going to do is say reset index and then give it a name, which is number of athletes. Excellent. So now that we have that, let's go ahead and also just show this over here. Cool. So now this is the same data as over here, but it's just in a data frame instead of in a series over here. We could have made the series work, but I generally just like to work with data frames. So I converted it to a data frame over here. Okay, so we now have 2 tables. We have per country counts over here. We also have medal totals. Or what did I call it? Medal counts. Okay, cool. So we have these 2 things, and now you'll see something kind of cool. We have in each row, we have a country code. Over here, that country code is AFG, ALB, ALG, which is just a 3-letter string that combines these things that sort of uniquely identifies each particular country. So what I'm now going to do is I now want to basically say, okay, go ahead and for each row in this table over here, look up the country with this country code and add the number of athletes to this table over here. Pandas makes that real easy too. So what we're going to do is we're going to say medal counts. Well, actually, let's say number of athletes and medals per country. Pretty verbose variable name, but we'll go with it. We're now going to say, okay, go ahead and give me medal counts. What I want to do is I want to merge my medal counts with the country counts. And the column I want you to pay attention to is the country code column in each of these tables over here. So I can say something like on is equal to country code. I think, I'm pretty sure this is how you do it. Excellent. That'll break. I got scared. This again is the kind of syntax that like I forget every time I write pandas, so I usually have to look up. So I'm glad I didn't forget. But now if we take a look at this table, excellent. We now have one table which says that the USA won 126 medals, but lost, but had 619 athletes. So this is very analogous to a few other things that you may have used before. If you've ever used like SQL, this is called a join of two tables in SQL. In database language, this would be called a join. In Pandas, it tends to be called a merge, but people would understand if you called it a join. If you use like Excel or numbers or something like that, I think this is kind of similar to like a VLOOKUP or HLOOKUP or something like that. I never remember which is which. But yeah, it's a really nice way of kind of combining a bunch of different things. Someone asked if this is like a pivot table. Unfortunately, I forgot what a pivot table is like 5 years ago. So I'm sorry, I'm not able to answer that. If we've got time at the end, I'm happy to Google it and answer that. But what I do want to do now is actually sort of do that analysis I was interested in earlier, which is create a new column. We'll call it like medals per athlete, which is equal to the number of medals, that the country won divided by the number of athletes. Sorry, I copied and pasted the wrong thing. I'm gonna put this on the new line so it's clear what I'm doing. You'll also notice that I'm kind of very inconsistent about whether I use like the dot syntax over here or the sort of dictionary syntax over here when I'm referring to my columns. It really doesn't matter. The only time it makes a difference is if there's space in your column name, in which case you have to use the dictionary syntax. But anyway, I digress. We go over here. We'll now see. Oh, okay. Apparently it did matter. So let's go ahead and change this to that. Excellent. We now have a new column over here, which is how many medals on a per athlete basis each country won. So now if we take a look at what this looks like, we could maybe plot this in ascending, we can maybe plot this in descending order. So we can say something like, okay, go ahead and sort by the number of medals per athlete, do it in descending order. And then we can plot, I don't know, maybe the top 30 of them. Dot plot. And that we let's say something like dot bar, because I think a bar chart makes sense over here. Then we can say that our X column is the country. And our Y column would be medals per athlete. I really hope I got that right. Invalid decimal literal. What did I do wrong?
Head 30. It's 30 right now.
Ed,
Oh,
Ed,
thank
typo.
you. And that would have taken me forever to figure out. Thank you very much. Excellent. Okay, cool. So, this is interesting. So it looks like no country score like more than one medal per every 2 athletes. So St. Lucia actually really wrapped 1 athlete every 2, followed by North Korea, followed by Kyrgyzstan, and then coming in 30th was Ecuador. If instead we just plotted the total, I think this graph would look very different. Total. Yeah, so you'll see, oh, sorry, this should just be total as well. Yes, you'll see that this graph looks very different with kind of the countries that sent the most athletes coming away with the most medals. Oh, interesting that there was also a tie between the UK and Australia. Alrighty, so that's PANDAS. I hope it's given you some sense for how you can sort of explore your data and do math and provide visualizations on that data. I think it's like really important. It's probably the scientific Python tool I use the most. And I hope those of you who are like already researchers can kind of see a use for like visualizing your own data over here. Everything I've done has been relatively simple as PANDAS goes. You can have really sophisticated visualizations and do really complex math on it as well. So I'd really encourage you, if there's like a research or science problem that you're trying to solve, to think about how PANDAS might be helpful with you in your tabular data. Okay, I know we don't have very much time left. That's actually intentional. I didn't want to spend too much time writing Matplotlib code because I don't think it's like a super, it's not a super common thing for a lot of people because they'd be using libraries like NumPy or like they'd be using libraries like Pandas instead. So what I did is a little ahead of time, I went together and actually put together a quick notebook of some Matplotlib code and the kinds of things you can do with it, just to give you a sense of like what's possible over here. So what we're doing now is kind of writing raw Matplotlib code. It's not necessarily the code you'd write if you were ever writing Pandas or so forth, but I want to kind of give you a sense of the options you can control if you needed to. So for instance, you can draw pie charts like I already showed you. And the important sort of line of code over here is this one over here, which is basically saying, draw a pie chart where each slice is sized according to this over here. So the first slice is 35%, followed by 25%, then 15%, 15%, and 10%. The labels should be Python, JavaScript, C++, Java, and Ruby. This is just some totally random data. I made it up. It's not actually true. What you can do is set the dimensions of your charts. You can sort of pop out a particular part of your chart by saying, you know what, the first one should be exploded out by a factor of 0.1, but nothing else should. You can set a title on your charts and so forth. And the other thing you can do, which is kind of fun, is you can actually save your images. So you can say, for instance, save this as a donut chart. I don't know why it's saying donut chart, but whatever. But if I run this now, it saves my image over here. Oh, sorry, I need to comment out the other one. Now, if I look at donut chart, you'll see that the image shows up over here. You can do more complex kinds of charts as well. You can do what are called stacked pie charts instead, where essentially you can like take a bunch of different time series and put them on top of one another, like I'm doing over here. So if you're trying to visualize like product sales or something, again, over time, you can do that, again, using here. Someone asked what library you'd use to visualize 3D stuff. I am so glad you asked that, because that library is Matplotlib. You can, in fact, also plot 3-dimensional data in Matplotlib. So you'll notice over here that I have an x-axis, a y-axis, and a z-axis. And then when I create my scatter graph, I'm saying, okay, give me X and X-axis, give me a Y. Whoops, I don't know how that happened. Give me Y fields and give me Z data. And what I had to do a little earlier on is say, actually, please do this as a 3D projection. So when I run this code, I get my 3D visualization of all of my data, which is, to me, incredibly cool. And the reason I think this is incredibly cool is it's actually interactive. As I'm moving my mouse around over here, you'll see down here what the values of X, Y, and Z are. So for instance, you'll see that like this purple thing is at X equals 0.83, Y equals 0.32, and so forth. But what I think is even cooler maybe than this is you can drag this around to look at your data from another angle. And this just comes totally for free from Matplotlib. I will say that like over here in a Jupyter notebook, you need to have these two things installed in order for like the drag and drop and the scrolling and stuff to work. So that's why I asked you all to install those earlier. There was a method to my madness. But yeah, you can totally do 3D plots over here as well. You can also do contour plots instead, which are basically plots wherein if like your Z function, if your Z variables are a function of your X and Y variables, this is, you know, like you can have a type of graph that does that, which produces the fun looking graph you saw in my slides at the very beginning over here. So my point over here is not that like you absolutely should be able to buy memory, do all these things. I Googled a lot, especially while I was doing these 3D visualizations, but I want you to have a sense of exactly how you could do these sorts of visualizations. The resource I want to point to you at over here, which I think is really helpful, is, again, if we go to the Matplotlib docs, Matplotlib documentation, so they actually have a really great example section over here where like it basically shows you all the different types of graphs that you can draw and so forth. So I'm sure they probably do have 3D graphs somewhere, but yeah, there's literally this many different examples that you can do over here. So if you're a researcher trying to figure out some way of visualizing your code, definitely check this page out over here. I'll send it in the chat right now so that everyone can see it. And yeah, feel free to poke through that because Matplotlib is, again, an immensely powerful library. So with that, that brings us to kind of the end of the tour of scientific Python I wanted to give you. I hope you haven't, if not a sense for what code you would write, what kinds of problems you can solve with these tools, and importantly, why these tools probably are the right ones to solve it. Like, can you imagine drawing this graph with like the Python graphics library in the Python ed, in the Python IDE online? I cannot imagine how painful that would be. So yeah, I will say these aren't necessarily everyday tools for you. The kinds of things like lists, dictionaries, functions, decomposition, those are very much everyday practices in Python. These are tools for specific use cases. So keep that in mind. I would love to hear if in the future you end up making anything cool with any of these things or choose to, you know, explore more scientific Python libraries. I love hearing what people do with their infinite imaginations. But I really do appreciate you taking this time to sort of spend with me and chat about all these different things. I am more than happy to stick around for as long as we want for people to ask any final questions or be it about this or anything else. But with that, I will call it. Thank you very much, everyone. I hope you enjoyed.
Hey, Bram. So I have one question and a comment. So when you're dealing with data frames, especially merging data frames in Python, and so same basic questions, if you have two data frames of different dimensions, is that not going to work? What would pandas do?
Yeah, great question. Sorry, let me quickly ask you a question before this. The notebooks that I've put together and this Matplotlib one. I'm gonna send those to you after this is done. Would you
Yes.
be able to distribute these to everyone?
Yes. You know, it's great that you brought that up because I kind of forgot about that. Because you did it in Jupyter Notebook. And then I know Jupyter Notebook, you could knit it into an HTML file, or a Markdown file. And then I had emailed you and then asked you what the differences were between those two files. But I was going to ask if you could send me the code. I will make sure people get them.
Yeah, absolutely. I'll send you both. Sorry, dropped my water bottle. I will send you both the notebook code as well as like PDF versions so people can just read them by themselves. Yeah, I'll make sure to get all of that to you. Apologies for missing your email. It's been a busy week. I did
Yeah,
see
no,
it.
no,
I
no,
haven't
no,
had time to
no.
reply yet.
No,
Okay.
I'm super grateful you actually took the time to be here today.
So to your question now on data frames, it really depends a little bit on, actually, if it's okay, I'm going to stop sharing my screen just so I can look at the Zoom gallery, even if I can't see your faces. So it sort of depends a little bit. There are a couple of different ways you can combine data frames. You can do what I did, which is sort of the lookup merge, for which your data frames don't need to have the same dimensions, because you're doing this like lookup join sort of thing. What you can do instead is what's called like a concatenation of data frames, which is where you basically like append them either horizontally or vertically by like stacking them together. If you're doing those things, then yes, they do need to match. Like if you're adding all the columns in one to all the columns in another, then they need to have the same number of rows, and vice versa. That said, if they don't have the same number of rows and columns, there are ways in Pandas to like essentially just pad out your data frame to like fill out the missing ones with zeros or whatever. So it does exist, but it depends very much on like exactly how you intend to combine two data frames, because you could do everything from like adding them on top of each other to like left and right, up and down, or like the lookup join that I showed off. So it depends a little bit on exactly what it is you're trying to do.
I see. But okay, because if you're dealing with like large scale data, right? Sometimes you don't really know where that missing data is.
Yeah.
Is there like ways in Pandas that Pandas can highlight for you where that missing data is so that you can quickly do a search and then see if the missing data correlates with I think like a particular row or a column
Yeah, absolutely.
that you might be missing.
You know what? Let me reshare my screen. Just so I can show you that. That's a really great question. Excellent. It's weird that I can't like also see a Zoom gallery, and I've got two monitors. Like whatever. I'll stop complaining. Okay, so there's a couple things you can do to answer your question. So for instance, let's take the height column, or you know what, athletes df. Now I remember _df. Okay. So for instance, you know, we have this column over here, the family column, where there isn't a data or whatever. So let's go ahead and look at just family athletes dot family. So there are functions dot is na, I think is one. Yeah, which basically says whether there's data in this column or not. So this is a quick way to like just find out all the stuff that all the things that are missing particular fields. So I can say, for instance, okay, give me all the athletes for whom I don't have family data. Athletes. And boom. So now I have all the athletes for whom my data is missing. So that might be one way you can quickly filter your data to see like if there's any like specific things that are missing. Another point I can make is when you're doing joins in particular, what I did is what's called, again, I sort of get this confused all the time, but it's what's called a left join, where basically, where is the join? Give me 1 second. Yeah, okay, so you'll see over here. Where is the, okay, yeah. So we kind of have, on the table on the left is medal counts. The table on the right is per country counts. So what we're doing is a left join where basically we are saying, okay, for each of the rows in medal counts, the stuff from country counts, but like otherwise ignore everything in country counts, like ignore any countries that didn't get medals. We can't change that around. We can't say something like this. I don't actually know if this will work, but okay, yeah. So that did the same thing because there were still medals, but there are ways in pandas to do what's called like a right join instead, which is basically going to say, okay, keep every single country, but just fill out zeros for all of the countries that didn't get any medals. I can't remember off the top of my head what that parameter is, but I'm sure if I outer join. Yeah, so what I was describing is called an outer join, and code for that is silly of me. Okay, it's just how equals outer. I did actually know that. I didn't give myself time to think. How is equal to, yeah, it's not left and right. The kind of join I did earlier is what's called an inner join, where I only kept the rows for which there was data on both sides. If I do an outer join instead, yeah, here's all of our countries, and you see like Vietnam, for instance, is in there even though it doesn't have any medals. So like if you are missing data, like you're not sort of bereft. You do have approaches you can use instead.
Thank you.
Yeah. Any other questions? Feel free to unmute, or I will keep looking at chat.
Is there a way to use a kind of a translation tool from SQL to Pandas?
Oh,
The left
yes.
joins or outer joins or stuff like that.
Great question. So short answer is yes. There's a couple of things. I'm trying to list them in order of how much I've used them. Typically, like personally, I am better at pandas than I am at SQL. So there are ways you could like take a SQL database and read it into pandas. So I'm not going to be able to write that code in a rush because I don't have a SQL database handy, but yeah. So essentially what you can do, and for those of you who haven't worked with databases before, don't worry about this at all. What you can do is you can like provide a database connection to a SQL database as well as some SQL query. And what Pandas is going to do is it will execute that query on your database and then read it into a Pandas table for you. So you can kind of do all the nonsense I've done over here. There is a Pandas library which allows you to like query your Pandas table like it's a SQL database. It's a separate library though. I think it's called Pandas SQL library. I may have to find this off because I've never used it myself. Yes, here we go. So it's called Pandas SQL, not a particularly creative name, but yeah. So you'll notice over here that you can create like a SQL data frame instead of a normal data frame. Then you can query it with SQL over here. But I don't personally like SQL, so I don't do that very much. But yeah, thank you for the question. I'm sorry I missed it earlier. Anything else people are curious about?
Well, Bram, this is not anything about programming, but I just wanted to make a comment. Last time when we had the API lecture, we actually had TJ. And then after TJ gave the lecture, I didn't realize like what a cult following TJ had. And he actually got like a marriage proposal on the like Discord service. Okay.
That's great.
Okay, and we kind of have like a code in place, fan club. And then somebody during your lecture, okay, actually privately messaged me. I think this person wants to remain nameless, and then I will say it's not me. But the person said, what did the person say? Let me see. Oh, wait. I gotta find it in my chat. Sorry. Okay. He's amazing, but I'm too shy to propose to him. So I offered I will do that. You don't have to have any kind of like response, but I just wanted to like throw it out there. You have your own cult following too. And then the other thing that I wanted to like throw it out there because you know, definitely our study section will be probably wrapping up in the next like 3 to 4 weeks. I know there are other people who are interested in continuing learning. I don't think I have it in me to ever become a programmer. I've learned probably enough that I ever wanted to know. But you know, I don't want to offer you up, but you know, if you're willing to like help in the future, on a periodic basis, maybe, you know, you can think about it and then maybe whoever is wanting to continue and learn other things about CS could contact you. Because Maron had told me you can probably teach anything about anything CS related that we would ever wanted to know. So
That's very, very touching from Maran. Thank you for all of that, first of all. I want to quickly touch on like what to do next and like what to learn next and so forth. So before we get to like who can teach you and stuff, I think there's a bit of a trap you can fall into when you're learning to program. Online on like various programming communities, it's called tutorial hell. I really don't like that name because tutorials are not bad. People put a lot of effort into both writing and learning from them. But I think there is a tendency though to like think that the best way to move forward is to like learn something new. I will say, based kind of on my understanding now of where you're at in your Python programming journeys and stuff, I'd say one of the best things y'all can do for your own journeys right now is to make something yourself. It doesn't need to be like a complicated thing. It doesn't need to be a thing other people will use. But like, if you just think about the tools that you've kind of been exposed to, even just in the past few weeks, like you now have a sense of scientific Python and data processing. You have a sense of APIs and how to do stuff over the internet. You know how to program in PyCharm rather than the code in place IDE. You basically have everything you need now to write a program that deals with the real world in some meaningful way, you know? And I would strongly, strongly recommend that before you move forward, you work on a project like that. Like give yourself a month, 2 months, something like that. Pick a project and really just like execute on that for a couple months. Set yourself weekly goals, maybe work on it in a group and things like that. And I encourage you to do that for a couple of reasons. First of all, I think it's far, far, far more satisfying than just getting to the end of a tutorial or an online course or whatever, but also because I think it will give you a better sense of what you want to get better at next. You know, like you could work on a project and be like, you know what, this was really, really cool. I want to just make more cool Matplotlib visualizations, and I want to learn more about pandas and data processing. You can just like send it on that and learn next about that. You may instead be like, you know what, the data processing was fine. I can do it. I mean, may do it again in the future. But what I'm blown away by is like how fast NumPy is. And I want to understand how to write my programs this quickly or like faster using things like NumPy. And so you can go ahead and like pursue that instead of, you know, bothering with the data analysis stuff. Someone else may be like, you know what, all the stuff was boring. I want to just make a website, and you may need to like go learn something new for that. So I think now is the time where it's on you to like decide what you want to learn next before it gets taught to you, if that makes sense. CS 106B, which is sort of the natural next step, just as like some context over here. I've taught CS 106B a couple times as a TA. CS 106B is kind of like delving deeper into how programs work. So it's understanding like how lists work and how dictionaries work under the hood and creating your own of them, which like is great, super powerful, super important to like, or not super important, super interesting to understand. But being very frank with you, like the code I wrote in CS 106B, I've been a software engineer, a professional software engineer for more than 4 years now. I have never written a CS 106B program in anything I've done at work. I have written CS106A programs in stuff I've done at work, because a lot of the time that like sort of diving more deeply is just not what you need to be a professional or semi-professional programmer. And what's way more important is building on top of 106A material rather than going below. So anyway, that's my sort of large spiel as to don't do another class just yet. Teach yourself for a little bit. Also, after 5 weeks of code in place and 5 weeks of code in place version 2, you deserve a break. So do that as well if need be. But when it comes to like learning for me and stuff in particular, I'm touched. It's hard for me to make sort of a longer commitment right now, but you know, I've really enjoyed doing this. I'd be more than happy to kind of help out on like a spontaneous basis wherever I can be helpful. But I think you're sort of at the point now where you like one of the challenges you should set yourself is being able to follow along with like the plethora of resources that are online. You know, you're not always going to need a teacher, and as we get larger, like the problems you're going to be interested in solving won't be like as general as the ones I've taught about today. You know, like at some point you will be the experts on your programs and you'll need to teach me how they work. So I'm not always going to be able to teach like a lecture on like everything you need to know. But yeah, that's my very long-winded response to that particular question. Yeah, specifically on the stuff I've talked about today, I think probably the most interesting way to move forward, the way I would move forward from this, is by going through that like list of pandas, list of Matplotlib examples, and like finding a cool visualization there and being like, okay, I want to make that visualization about something else, and then working backwards from there to see like how you can get the data set, how you can turn that into pandas data frame, how you can turn that into a Matplotlib visualization after that. So yeah, there is your next step if you need a specific next step. Anything else from anyone?
You mentioned you don't like SQL, but I understand SQL is necessary for data science. What are your thoughts on that?
Great question. I said I don't like SQL that was probably not as much detail as I should have provided. I'm less comfortable writing SQL than I am writing pandas, meaning that like if I need to quickly do an aggregate or like get some information from a data, it's generally like much faster for me to like turn it into a pandas data frame and do everything I need to do in pandas. Most of the time I'm doing this for work, and at work I have like a very powerful computer, so it's very fast and I don't typically observe slowness from not doing it in a database. But to sort of, if you plan to be a data scientist or like meaningfully do data science as part of like whatever you want your life to be, it is still crucial that you learn SQL and that you use it. It's not like going anywhere. So yeah, SQL, for those of you who don't know, SQL is kind of the language by which programmers and engineers interact directly with databases. So where I used Python to like query stuff in my pandas data frame, you would use SQL to query stuff in your database. So when I say I don't like SQL, I just mean I'm slower in it. And I reason more intuitively in Python, but I don't think there's anything inherently wrong in it, nor do I think you shouldn't learn it. And I know many engineers who like prefer to live in SQL than in pandas. Good question. Thank you for calling me out on that. Anything else from anyone?
I have a question. Hi, Bram. Thank
Hi.
you for your lecture. I mean, it was really nice of you, and also thanks for the work you do with Code in Place.
My pleasure.
So I was trying to look for this tutorial how, but I'm not finding anything. Is this escaping tutorial hell? That's what I'm getting from Google. So if you
So tutorial hell isn't like a website or whatever. Tutorial hell is when people just keep doing tutorials rather than like doing their own thing.
okay.
So if you found tutorial hell on the internet, I would stay away from it anyway. But yeah, tutorial hell is a condition, not a website.
Okay, thanks for the clarification.
No worries.
Brahm, I had a really small nit thing about Jupyter notebooks.
Sure.
After doing one, I wanted to get a copy of it, and it says that you can export it to PDF, but
Yeah.
it doesn't work. So I exported it to HTML, and I could copy
Yeah.
that. But does it simply not work to export directly to PDF, or am I doing something wrong?
You know, I have a suspicion I know what's going wrong. Let's debug this together. And you know, pandas is something I know how to do. This is not something I know how to do. So let's see if I can figure it out real quick. File, save and export as PDF. Okay, yes, this was my guess over here. Pandoc wasn't found. So Pandoc is another program that is basically responsible for taking one type of document and converting it to another type of document. So if y'all will bear with me, I can sort of do this now. Yeah, okay. So it'll give you like instructions as to how to install this on each of your machines. Hopefully they have Windows instructions. Yes, they do have Windows instructions as well. So if you want, I can just do it now to sort of convince ourselves it works. Give me 1 second. Brew install Panda. Okay. So yeah, basically what this error means is it's complaining that like Pandoc wasn't found on my computer, so it can't like use Pandoc to convert it to a PDF. Brew might take a minute to install it, so when that finishes, I'll carry on that thread. But yes, I was anticipating having to do some work to convert it to a PDF. Anyone have any other questions or wondering about anything else about code in place or whatever? You know, you all have done code in place. I've been in the background of code in place for a while. Happy to talk a little bit about that if you all are curious.
Can you talk about the difference of what a markdown document is in terms of the Jupyter notebook?
Yes, yeah. That also may depend on having Pandoc installed. So let me quickly test that hypothesis before.
I think like markdown document is something used with certain IDEs,
Yeah, kind of. Let me.
like with I think RStudio, but I don't know if their function exists beyond that.
Yeah, good question. Okay, so so just for context, I installed Pandoc, and I tried exporting as PDF and to HTML and sorry, and to Markdown. It seems like it was complaining about something, so I might need to debug this offline. But I promise you, I will get you all your PDFs and I will get you an explanation of what went wrong. Okay, so Markdown, real quick. So Markdown, kind of just another language for writing documents. So like, when you write Microsoft Word, there's like a set of things you can do to like make bullet points and turn things bold and so on. Markdown is just like another document format for text documents. So let me go to some code that I've written a while back. You don't need to worry about GitHub at all or anything. I'm just trying to. Oh, you know what? Here's something that might be fun. Yeah, okay. So here, I'm afraid you won't be able to access this page because it's secret. It's like hidden behind an account thing, but okay. This is all of the code for Code in Place. So the website that you all go to on a regular basis, this is the code for the website. So you'll see, for instance, TJ is out here adding some like changing some stuff about it. And there have been at least 25 people who've written code for just this website. There's me over here. Okay, so you'll notice there's a document over here that outlines how to like install and set up programming for this. Don't bother about reading these instructions. They won't work for you, I'm afraid. But this is a document that's written in Markdown. So this is the syntax for Markdown. It's basically saying like a big hashtag over here means that this is going to be like a big header. 2 hashtags mean a slightly smaller header and so forth. So basically Markdown is a way to like describe what your document should look like and then it'll render it. So for instance, I can say, this is a demo of Code in Place. This is bold text. And this is also formatted, and this is code. And now, if I go to preview, yeah, you'll see there's a text I just added, which is formatted as I wanted to. So like, I don't know, I wouldn't say Markdown is something you necessarily need to formally learn. There will come a time when you need to edit a Markdown document, but it's like, I think pretty obvious how Markdown works. So you just sort of open up the document, you write whatever you need to, and then you save it and it renders correctly based on whatever. So yeah, that is that. Let's see what went wrong. Oh, I know what went wrong. That was silly of me. 1 second. Oh no, actually, sorry, no, I'm still debugging the PDF thing. I'll keep doing that. But I'll stop sharing my screen so you don't have to. Okay, there's just like more stuff that will need to be installed and so forth. So I'll do this offline, but I'm pretty confident to answer your earlier question that you just need to have stuff installed so that Jupyter is able to convert this into PDF.
So Bram, this is my only opportunity to impact Code in Place. So, by the way,
I would argue you impacted it by joining it, but
I thought it was a fantastic course. You know, the one thing that drove me crazy was the auto checker, and then you kept updating it, and then we didn't know whether it was working or not working. And I found it really helpful in the beginning of the course because I would sometimes think I got something right, but the auto checker would say, no, you didn't. And in fact, I made an error. Now, sometimes it was a little nit or a period or whatever. So I was fine with that. But what was really hard is not knowing if it was working or not for a particular problem. So if there's any way in the future to give students a heads up when this won't work with auto check, don't worry about it, that would be helpful.
Awesome. Yeah. Thanks for the feedback. I'll definitely keep that in mind and relate to the rest of the team. Code in Place is always a work in progress, so there are rough edges, but we are doing our best to smooth them out when we find them. Cool. Anyone have any other questions about Code in Place or anything else?
I have a question about the way you actually did us show the how to use the project on our machine with the Virtual Studio Code, right?
Yes, yeah.
I know that there's an option to use it on the cloud on GitHub in the mode of the like in the browser, but for some reason I'm struggling with the Jupyter notebooks in there. Could you please show us how to do that in VS Code?
Yeah, absolutely. So it's actually nothing, it's not too complex, fortunately enough. Okay, so let me quickly show you what's going on over here. Okay. So right now on my computer, I'm in a folder on my desktop called Learning Scientific Python. Learning Scientific Python has those two notebooks.
Do you want to share your screen again, Bram?
Oh, shoot, sorry.
We're only seeing you. We're not seeing it.
Yeah. You mean you couldn't just picture what was on my screen?
Yeah.
All right. Okay, so I'm in my terminal right now, and I'm in a folder on my computer called Desktop Learning Scientific Python. It's a folder I made just for this lecture. And inside this folder, I have untitled.ipynb, which was my my Matplotlib notebook, sorry, my NumPy notebook, and then untitled 1.ipynb, which was my Pandas notebook. I should have given them better names. And then we also have that data directory, which was like all of the CSV files I saw. Okay, so basically all that needs to happen is I need to edit, I need to in VS Code, I need to go ahead and open a folder in VS Code. I'm going to go to my desktop, I'm going to open up Learning Scientific Python. Click open. And yes, I trust the author. I know him quite well. And okay, so now you'll see over here, we've got those two notebooks over here. And if I click this one, it'll show up in VS Code. I might have an extension that does that for me. Let's find out. Okay, yeah. So there is an extension for Jupyter Notebooks. I think it comes pre-installed on VS Code, so I don't think you'll need to do anything specifically. But VS Code already knows how to deal with Jupyter Notebooks. So all you need to do is open up your IPYNB file over here, and then you can just run your Python code, which I do by hitting Shift Enter, but you can also just like hit the run button over here. So I'm going to hit Shift Enter. It'll then ask you to choose a kernel source. I can go into like what a kernel is and stuff. It's pretty complicated. But basically, if you just click Python environments, I have a lot of Python environments. You will probably only have one. So click that one. It may ask you to install something, so you should install it. It'll take a second to do that. And then you can start doing all of this over there.
I'm
I
sorry,
actually
Ram, but
chose the wrong thing over here.
You are
So-
actually, you have your thing called Jupyter Lab on your local machine, and then you opened your just in your
Yeah,
local
so
environment. But I'm asking about the VS Code on GitHub on the cloud, so we can
on
use
GitHub.
this.
Oh, I'm sorry.
Yes, yes. I'm sorry too, because it's like a little bit different. So we don't
No
have to
worries.
be actually confined to a local machine, but we can do it.
Great question. You know, I don't know. I don't think I've done that before because I always do it on my own computer. Let's see if I can figure that out. This is a random thing that should have some notebooks. Yeah, okay.
The reason why I'm saying this because I know that there's this thing called code spaces on GitHub.
Yes, yeah. I do know that too. I've unfortunately never used it myself. So let's see what I can find over here. Okay, let me quickly spin this up and say GitHub codes. Okay. Get started for free. That sounds good. Okay, Jupyter Notebook also sounds good. Oh, cool. I've actually never used this before, so you're teaching me something today. Okay, let's take a
It's
look
kind of
at
hard for me to drag my iMac to a bomb shelter here in Kiev because we have air sirens. So I kind of you have to get a little bit innovative to actually do stuff here.
No.
Sorry.
I totally understand. I deeply appreciate that you're still working on all of this stuff
Just
from
being
there.
real as it can be.
No. This is great. So okay, this is great because I get to learn about this tool as well. Okay, so I did just create a Jupyter Notebook code space over here. It seems to have shown up over here. And yeah, okay, so this looks largely like the ones we've got already. What I'm going to do is I'm going to go ahead and create a new notebook. Let's call it test notebook.ipynb. Okay, cool. And now, let's just try importing the three things we tried today. Import Matplotlib, Python environment.
On the
so
top right, we have the selection of the kernels, and I believe this is.
oh
where
yeah. So that should do
Yeah.
the same thing. Let's do it that way instead. Select kernel. Yeah, it'll take you to the same Python environments. Select this one. And okay, cool. So the Python environments already have this set up, it looks like. So yeah, you won't need to install anything if you're using the Python environments. Should just work out of the box. Was there a specific issue you were running into that I can help?
I was just wondering, it just for some reason, I was wondering just the way you have been choosing the type of the machine or the type of the kernel, and it seems so so just
Yeah.
just one
okay.
for you to choose, right? So just
So
asks
maybe
you.
let me explain what's going on, like what the kernel is. Like I think that'll make things a little easier. Okay, so clearly Jupyter in some ways understands Python, right? Like I can write like print pi over here and it understands it and so forth. But it's not the same as running a normal Python program, right? Like it's not running in one continuous thing. It stops and waits for me to type something, change some code, but it also somehow like remembers my variables in between me running Python code between executions. So the kernel is kind of, you can think of the layer between the stuff like your Jupyter notebook and the actual Python interpreter. So what that means is that the kernel is the thing that remembers all the values of your variables. It remembers like what your code last looked like and what it's going to look like in the future. And then whenever it needs to execute Python, it goes ahead and executes the Python for you. So what that means then is you can have many Jupyter kernels on your computer, each of which like is tied to a different Python. So one of the implications and one of the sort of like weird things you may not never ever really need to play with is you can also have a bunch of different Pythons on your computers. So just as an example, like software engineer, I do a lot of different programming projects. And so I have like different Pythons on my computers with different packages installed and stuff, just so like nothing is conflicting with one another. And then if nothing is conflicting with one another, and because I have different Pythons, I also have different kernels on top of those Pythons. So like I'll have one kernel for code and place work, one kernel for work, one kernel for like this lecture that I delivered today. So that's why I have to like go through a bunch of pain to like decide which kernel to use and so forth. You, on the other hand, as you're like developing, I would strongly recommend not worrying about that for now. So it looks like the VS Code kernel in code spaces, for example, there's only one Python. So you only need to worry about this one thing. So like when you're asked to select a kernel, just select the one that comes with the box. And it looks like it has a bunch of libraries already installed over here. Let's see if I can find what the other ones are. Oh yeah, there's like a ton of libraries over here. Basically anything you'd want to do in scientific Python, you can do over here. So for your
Yes,
purposes, just select the
and
default
actually
kernel.
the way I asked is because we normally like use the data and it's somewhere on the cloud. So it's actually much easier to just use the
Yeah,
machine on the cloud too.
totally. Yeah, no, that makes this is a really great tool. I have never used it before because I'm just used to using the tools I use, but no, this is awesome. Thank you for putting me onto it, and I think it's a totally effective
Thank you
way
for
of
showing us.
working on this.
Mhm.
All righty. Anyone have any other questions that they're curious about? Stories they're interested in hearing?